Good evening to all. My name is Ganesh Shankar Bhandari, and I am the TA for the NPTEL course Principles of Casting Technology taught by Professor P.K. Jha, IIT Roorkee, and I am going to take the live session for seventh week for the course, and we will start. We will wait for 5-10 minutes. We will see if anyone joins. Then we will start. Hello Nagendra, we will start in 5 minutes. We will wait for 5 more minutes. If anyone joins, then we will start. Okay, so we will start with today's live session. Yeah. So we are going to read about iron carbide phase diagram. Okay. So you have already read about iron carbide phase diagram and heat treatment processes of iron, mild steel, and cast irons, how to make different types of cast irons. So the making of all cast irons and all types of mild steel, either it is low grade carbon steel, medium grade carbon steel, or high grade carbon steel, it depends on the iron carbide phase diagram. Okay, whatever type of properties you want in your steel, either you want more ductility in your steel, or either you want high hardness in your steel, you have to keep this iron carbide phase diagram in your mind. So as we can see in this diagram, there are different types of phases given. Okay. Okay. So as we can see, the common phase which we seen in day-to-day life, which is basically mild steel. Okay. So okay, you are not getting it. You are able to see the. Okay. 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 1 second. So now you are able to see it. Okay. Okay. So as we can see here, this is alpha ferrite plus perlite phase, which is basically you can say it's a phase of mild steel, which we use in our day-to-day life. Either it is TMT bars or it is mild steel sheets or something else. Okay, so that is the common phase of alpha ferrite plus perlite, which is present in your mild steel. Okay, so it contains around a carbon percentage of 0.8%, not more than that. If you are going to need some ductility and hardness at the same time. So we generally go with a carbon percentage of 0.23 to 0.8%. Generally, in TMT bars, you can find a carbon percentage of around 0.4 to 0.35%, not more than that. Okay. So if you are going to treat your mild steel above this temperature, okay. So here we can see that is the temperature is 723 degrees Celsius, and that alpha ferrite plus perlite phase is going to convert into austenite if we are going with the 0.8% carbon steel, and we are going to heat it above 723 degrees Celsius. Okay, so that is going to convert into your austenite phase. That we can say it is basically a meta stable phase of your in during your heat treatment of steels. Okay, why we are saying it as meta stable phase? Because that phase, this phase is not stable at room temperature. Okay, whatever, if you are going to treat the treat your steel at temperature above than 723 degrees Celsius, then you are going to get austenite phase. But as soon as you are going to cool it down, okay, so that austenite phase is going to convert back into your alpha ferrite plus perlite phase and iron carbide. Okay, or it can get converted into martensite phase also, that or bainite phase. That will depend on your cooling rate procedure. Okay, whatever type of cooling you are going to provide that sample, it will get converted into different types of phases. Okay, so as we can see here, that alpha ferrite up to 7 to 3 degrees Celsius, it is basically ferromagnetic and BCC type structure. Okay, it is the crystal structure is body centered cubic. But as soon as you are going to get converted that phase into austenite, the magnetic properties is going to change. Okay, that will convert it into paramagnetic, and you are going to get phase centered cubic structure. Okay, FCC structure. And if you are going to heat this austenite phase above around 1493 degrees Celsius. Okay, so that phase is going to again convert into liquid plus delta ferrite. Okay, the delta ferrite is basically the change structure of your alpha ferrite only. Okay, why we are saying is delta ferrite? Because a little changement will be there, but the crystal structure will remain same as your alpha ferrite and pearlite phase. That is also going to be your BCC structure. So when we talk about R1 carbon phase diagram, we mainly talk about 3 points. First is 0.8% carbon at 7 to 3 degrees Celsius. That temperature is basically known as your eutectoid temperature. Okay, eutectoid steel formation is there. Then second point is your around 2.06% carbon and at 1153 degrees Celsius. This temperature is basically your eutectic temperature. Okay, because at this temperature your solid is going to convert into two phases of liquid and one phase of solid. Okay, so this is known as eutectic temperature. And one more point is there, that is this 1493 degrees Celsius. That temperature is known as your peritectic temperature. Okay, because at this temperature one solid is going to convert into another solid and one liquid phase. Okay, so these three points are important during the study of carbon phase diagram. And as you can see here, we have black lines and we have dotted red lines. Okay, so when we are talking about iron carbide phase diagram, we are talking about carbon and iron. Okay, this red phase is basically for iron graphite phase diagram. Okay, when we are going to talk about graphite or we are talking about cast iron or like that formation, so we will consider this red line for the for calculating the temperatures and compositions of your cast irons. Okay, so as we can see here, until 2.06% carbon. Okay, the iron which is containing around 2.06 maximum 2.06% of carbon, it will be called as a steel. After 2.06% carbon until 6.67% carbon, that iron is going to be named as cast irons. Okay, cast irons can be of different types. It can be malleable cast iron, it can be it can be spheroidal cast iron, or maybe graphitic cast iron, like that. Okay, so whatever type of heat treatment you are going to give, you have to decide the temperature range according to this iron carbide phase diagram. Let's say if you want martensite in your system, you want very high hardenability with a HRC range of hardness range of around 60 or 65 HRC, then you have to go for martensite phase. Okay, so making that martensite phase, you have to treat your alpha ferrite plus perlite cementite structure above your critical temperature, which is basically this line, this 911 degree Celsius to 723 degree Celsius, G point to S point. This is your critical temperature line. Okay, that critical temperature is going to change according to your carbon percentage. When we are talking about 0.8% carbon, the critical temperature is 723 degrees Celsius. And if we are talking about 0% carbon in the steel, then we will go with 911 degrees Celsius. So we have to convert this whole phase into the austenite phase. So generally we go with the around 30 to 50 degree Celsius higher temperature than your critical temperature. Okay, if the critical temperature is 911 degree Celsius, then we will go with the temperature of around 940 or 950 degree Celsius for the heat treatment process. And we are going to convert that whole alpha ferrite plus perlite phase into your austenite phase, and we are going to quench it. Okay, so during that quenching procedure, this austenite phase is getting converted into the martensite phase. So whatever type of phase you want, you have to provide the heat treatment according to that procedure. And for heat treatment procedure, the temperature you have to calculate with the help of this iron carbide phase diagram. One more thing is here, uh, in steels, when we talk about phases, we generally talk about three phases mainly. First is perlite phase, which is nothing basically but just alpha perlite plus cementite uh, layer wise structure. Another phase is austenite. Then we come to martensite phase, and sometimes we also talk about banetic steels. Okay, bainite phase also there, but bainite is also, we can say, it is metastable phase, but you can't see that phase in the carbide phase diagram system. Okay, because for that phase, for creating that phase, you have to provide some extra efforts during your heat treatment processes that we will talk about later on. Okay, so when we talk about austenite phase, basically generally it is metastable phase, but we can create this austenite phase as room temperature also, because in some applications, some specific applications, we need austenite phase in our steels. Okay, so when we talk about austenite phase, we talk about surgical blades. Okay, in surgical blades, you have to make those surgical blades with the help of austenitic stainless steel. Okay, so creating this phase at room temperature. Okay, because what we are seeing here in iron carbon phase diagram system, we are getting this phase at more than 723 degrees Celsius, and we are when we are going to cool it, then it is again going to convert it into some other phase. So how we are going to get this austenite phase for making surgical blades and surgical equipment? So what we will do, we will add some austenitic stabilizers in your steel. Okay, so austenite is nothing, basically having FCC crystal structure. So we will add some FCC types of FCC having FCC cubic crystals, crystal structure elements in your steel system to make this alloy. Okay, so what they will do, they will put get this temperature down up to room temperature. So according to quantity of elemental percentage in your steel, this temperature is going to get down from 7 to 3 degrees Celsius to maybe 20 or 25 degrees Celsius. So you can get that austenite phase at room temperature. So in case of stainless steel, when we talk about stainless steel, we talk about austenitic type of stainless steel or pearlite type of stainless steel. So in case of stainless steel, we can create this austenite phase at room temperature also with the help of different types of alloying elements. Okay, so coming to next one. So now we will talk about different types of heat treatment processes. So there are five types of heat treatment processes which are generally used during the heat treatment of mild steel or cast iron. So first is normalizing. So when we talk about normalizing process, okay. So in normalizing process, what we are going to do, we are going to heat our temperature beyond upper critical temperature, and we are going to cool it in air only. Okay, we are going to put the sample in heat treatment furnace. We are going to uh, get the temperature, put it in heat treatment furnace according to our required temperature, and after giving the heat treatment process for some time, we are going to take that sample out from the furnace, and we are going to put it in air to get cool down. Okay, so that will be your normalizing process. So in case of normalizing heat treatment type process, you are going to get some ductility. Okay, more ductility in your sample. You are not going to get hardness in your sample. Okay, then coming to annealing process. Annealing processes also, we have to heat treat our sample beyond upper critical temperature. But the difference between normalizing and annealing process is that in normalizing process, we are taking that sample out from the furnace, but in annealing process, we are not going to take out the sample from the furnace. We are going to cool it down in the furnace itself. Okay, so in case of annealing, you are going for high ductility, very high ductility, but the strength of the sample will become very less. Okay, you can't talk about toughness. Okay, you are going to get a hardness of HRC of around 5 to 10 only, but in case of normalizing, you can get a hardness of HRC of around 25 to 30 also. Okay, so generally annealing process is applied on the steels which have gone through very high, you can say, plastic deformations. Okay, so during plastic deformation, what is happening, the stresses are generating in that steels due to plastic deformation. So relieving those stresses from that steel sample, we are going to analyze it. Okay, we are going to heat treat it beyond upper critical temperature, and we are uh, allowing allowing the sample to cool down in the furnace itself. So whatever the stress is present there, So those are going to removed from the sample by the grain refinement process. Okay, because in any heat treatment process, what we are doing, we are refining the grain size of the sample. Okay, when we talk about solidification process, we had already talked about the uh, grain size. Okay, whatever what types of grains are forming going to form there, it can be dendritic formation or it can be aqueous grain according to your solidification process. But when we are going to put that sample in some application, so we need homogeneous grains inside our sample. Okay, so we after casting process only we can't go for some we can't go for application purposes of that casted material. We have to go for heat treatment process to refine our grains according to our need. If we need very high strength in our sample, then we need some smaller size grains. And if we need very high hardness in our sample, then we can go with uh, bigger size grains also. Okay. Then coming to the third one, tempering process. So in tempering process, what we are going to do, the specimen is reheated to temperature below lower critical temperature followed by any desired rate of cooling. So the temp before tempering process, uh, for one process comes which we called as quenching process. Okay. So in quenching process, what we generally do, we heat our sample beyond upper critical temperature and we are cooling it cooling it down with very fast cooling rate. Okay, so providing that much of fast cooling rate around 100 degrees Celsius per second or maybe 150 degrees Celsius per second, what we are going to do, we are taking our sample out from the furnace and we are going to put it down in cold water or cold oil. Okay, so what will happen, due to very high conductivity of water or oil system, your sample is going to cool down very quickly. So we are not providing the time to sample to for the refinement of grains. So whatever the grain formation was there during that austenitic conversion, it is going to cool down like that only. We are not providing the time for diffusing out of carbon from the system or iron carbide from the system out. So whatever thing is there, it is going to cool down like that only. Okay, so in that case you are going to get very high hardness on your sample. The hardness value can be around 60 to 70 HRC. But if you need some stress relieving, because you are going to cool your temperature temperature of your sample down from 900 degrees Celsius to 25 or 50 degrees Celsius within few seconds. Okay, so what will happen, there will be very high stress generations due to thermal shockings. Okay, so removing those thermal shockings and very high stresses from the sample, you are we generally do tempering process. So in tempering process, what we are going to do, we are going to provide the heat treatment process again to our sample, but this time lower than critical temperature. So what was our critical temperature? If we talk about 0.8 degrees Celsius, we talk about 723 degrees Celsius. Okay, 723 degrees Celsius. So lower critical temperature, it's like we can go with heat treatment process at around 650 degrees Celsius or 600 degrees Celsius. Okay, so after that heat treatment process, we can go with any type of cooling process. We can go with normalizing or we can go with annealing process, whatever type of process we want. But we can't go with quenching process because we had already done that process. So that is known as tempering heat treatment process. So coming to next one, spheroidizing process. Spheroidizing heat treatment process we already talked about in our previous lecture. We talked about spheroidized graphite cast iron. Okay. So what we are going to do in that case, this type of treatment we generally provide with the steels having carbon percentage more than 2.06% because that comes under the category of cast irons. So when we talk about spheroidizing, suddenly cast iron comes in our mind, because we talk about spheroidized graphite cast iron. Okay, so the specimen is heated slightly above the lower critical temperature. We are going to heat it above the lower critical temperature and held at this temperature for some time and then cooled slowly in furnace. So what we are going, so when we talk about lower critical temperature, okay, so here we can see there are two lines. Okay, one line is from G to S, other line is from P to S. Okay, so if we are talking about upper critical temperature, okay, so that is the line G to S. This is upper critical temperature, and S to E, that we can say as upper critical temperature. Okay, because in upper critical, after upper critical temperature, your phase is going to convert into austenite. And when we talk about lower critical temperature, okay, so we talk about these lines, okay, from G to P and P to S, okay, and from S to K, that is our lower critical temperature. Okay, because in that temperature range your phase is not going to convert into austenite, but what you are doing, you are providing the time, sufficient time, for the presented iron carbide in the system to diffuse out from the sample. Okay, you are providing sufficient time for the diffusing out of iron carbide from the system. So what will happen after diffusing out of this iron carbide from the system, that is going to convert into graphite. Okay, because if it is breaking, then it will again convert back into iron and carbon, and that carbon is going to convert into graphite, spheroidal graphites. Okay, so when we talk about spheroidizing, we talk about lower critical temperature. So we are going to heat our sample above the lower critical temperature and held at this temperature for some time and then cooled slowly in furnace. So what we are providing? We are providing annealing process to that. So we are providing time for diffusing out carbon from the system, from the matrix of your iron carbide. Okay, then coming to next one, it is hardening process. We have already talked about quenching process, so that quenching process is also known as hardening process. So what we have talked about heating the sample above the upper critical temperature and holding at that temperature for some time and then quenching. It means cooling suddenly in within few seconds. You are going to cool that temperature down from 950 degrees Celsius to 25 or 50 degrees Celsius in a suitable cooling medium, that can be oil or that can be water, depending on the necessities. Okay, so these are our heat treatment, different types of heat treatment process. Now we will talk about, there are different types of annealing processes also. Okay, in case of normalizing or tempering, there are only one type of process. When we talk about annealing process, we talk about different types of annealings. Okay, so annealing process can be defined as four types, four different types of annealing processes are there. One is diffusion annealing, then full annealing, spheroidized annealing, and process annealing. So in case of diffusion annealing, what we are going to do in this process, hypoeutectoid or eutectoid and hypereutectoid steels are heated uniformly and the component is held at a temperature between 1000 to 1200 degrees Celsius and then cooled very slowly in the furnace in order to remove the heterogeneity in the compositions of heavy castings. So what we are trying to do, we are trying to homogenize the phase structure of our sample. Okay, so we can say this as homogenization process also. We can term it as. So to increase material properties, it goes through full annealing after diffusion annealing. Okay, and if we want to increase our properties, because what we have done, we have homogenized our sample, but we have gone gone to very high temperature around 1000 degrees Celsius to 1200 degrees Celsius, and we have broken the structure of our material. We have broken the iron carbide system into iron and carbon, both outside of matrix. Okay, so after, if we require to increase the toughness or hardness values of our sample, then we require full annealing after our diffusion annealing process. So in case of full annealing, what we are going to do in full annealing, we are going to heat the steel component to about 50 to 70 degrees Celsius above the critical temperature. So what was the critical temperature? That can vary from 923 degrees Celsius to 723 degrees Celsius. So above that line, we can add up around 50 to 70 degrees Celsius temperature. If it is with 0% carbon, then we have to go at temperature at around 1000 degrees Celsius. And if it is 0.8% carbon, then we have to go with around a temperature range of 800 degrees Celsius. So what we are going to do, we are going to heat that sample. We are going to give sufficient time for heat treatment process and cooling that down in the furnace itself. So this type of full annealing adopted for steel casting and ingots. So when we talk about ingots, we talk about continuous casting processes. Okay, so whatever type of ingots we are going to produce with the continuous casting processes, so homogenize their properties. Okay, we are going to heat treat them with the full annealing process. The coarse structure produced during solidification break down to a much smaller size. Machinability and ductility increases because we are talking about grain refinement. So grains will be very low, having very lower size. Hardness will be reduced, and all structural imperfection gets removed. Okay. Then coming to the next one, spheroidized annealing. So, spheroidized annealing, we have already talked about spheroidizing process. This type of annealing we generally provide for cast iron to produce spheroidizal graphite cast iron. Okay, so that is spheroidized annealing. Then coming to last one, process annealing. This process involves heating of steel to a temperature just below the lower critical temperature. Okay, so we are not going above the lower critical temperature. We are remaining below the lower critical temperature. So that will be that is 7 to 3 degrees Celsius. Then usually cold work steel has high hardness and low ductility, making it difficult to work. Okay. So what we have talked about, when we are going with the manufacturing processes like extrusion or maybe roll forming or cold rolling process. So what will happen? Those samples uh, will be having very high hardness values, and you can't, if you are going to create a sheet from your ingot with the help of cold rolling. Okay, so that cold rolled sheet cannot be directly used for the deformation processes. If you are going to convert that seed, like for example, if you want to make a car, okay, the body of a car. Okay, so what we will do, we will take a mild steel sheet and we are going to deform it according to our need in desired shape. Okay, so those seeds generally produced with the help of cold rolling or hot rolling of ingots. Okay, so during cold working process, what will happen? There will be generation of very high stresses in that steel. Okay, and due to that high deformation, that is going to provide very high hardness. Okay, so that is going to get some brittle properties inside that steel, and we cannot use that sheet directly for the deformation process. Okay, because for deforming that mild steel sheet, we need some ductility in our sample. Okay, so providing that ductility, we have to go with the process annealing process. Okay, so what we will do, we will heat treat that steel lower critical below the lower critical temperature, because we don't want to convert the phase into austenite. We just want relieving of stresses from that steel, so that the high hardness value of that steel becomes lower down. Okay, so what we will do, usually cold work steel has high hardness and low ductility, making it difficult to work. So deformed grains in cold working get reoriented. Okay, so what we are doing just doing grain refinement of that steel, and hardness is lowered. And during that, if hardness will lower, then obviously your ductility will get increased, because when we talk about hardness and ductility, both properties are vice versa to each other. If the hardness is very high, then ductility will be on the lower side, and if the ductility is very high, then the hardness will be on the upper lower side. Okay, so uh, after this hardness and ductility, one more word comes in picture, that is that we called as toughness. Okay, so when we talk about toughness, we generally talk about ultimate tensile strength or something like that. Okay, so toughness is basically the mixture of that hardness and ductility both. Okay, we can't say if any material is having very high ductile properties, so we can't, or having very high hardness properties, so we cannot dictate that material is having very high toughness values. Okay, for toughness values to be high, you have to optimize your hardness and ductility values at optimum. Okay, then only you can say that so and so material is having very high toughness values. Okay, because for example, if we talk about aluminium, okay, so that aluminium, any aluminium alloy you take, that is having very high ductility. Okay, but those alloys don't have very high hardness values, so we can't say that aluminium is a tough material. Okay, and when we talk about cast iron, that is having very high hardness values but very less ductility. So we don't say cast iron is a tough material. But when we talk about stainless steel or mild steel, we talk about toughness, because these alloys have a optimized hardness value and optimized ductile values. You can go with the applications which need very little bit of brittleness, and you can go with the applications of deformations also. Okay, so toughness is basically a mixture of hardness and ductility at a optimum level. So now we will come to some MCQ questions. Okay, okay, one more slide is here. So this diagram we call as CT diagram, CTC diagram. Okay. So here we can see we have three lines. Okay. One is this, one is this, and one line is this. So these three lines represents, as we can see, we have temperature on y-axis and we have time. Okay, logarithmic time values on the x-axis. So these three lines are representing the different cooling rates during the heat treatment processes of steel. So as we can see in this graph, we can see this line is representing eutectic steel. Okay, eutectoid steel, that is the temperature of around 723 degrees Celsius or 725 degrees Celsius. So if we are going to heat treat our mild steel above this temperature, okay, so we are going to get stable austenite. So here, why we are taking this line as straight? We are talking about eutectic steel having 0.8% carbon. We are only talking about eutectic steel as of now, zero point 0.8 with 0.8% carbon. So above 723 degrees Celsius or 725 degrees Celsius, we are going to convert our perlite phase into the stable austenite phase. Okay. So when we will talk about heat treatment processes, we are talking about three different heating rates. So first we can consider this one. So heating rate is the cooling rate is very slow. Okay. So we can say this is type of slow cool annealing. We are going to heat treat our sample and we are going to cool it down in the furnace itself. So what will happen? As you can see, this is start and this is the finish. Okay, so this is the starting of phase transformation during that cooling process, and this is the starting of uh, this is the ending of phase transformation from stable austenite to perlite. Okay, so as we can see in middle of this start and finish, we are having a mixed phase of austenite and perlite. So when we are going to slowly cool down our structure, so that will start the stable austenite conversion to perlite conversion will start from here around 50 to 60 degrees Celsius temperature lower than your critical temperature, and it is going to finish at this point. And as we can see, the perlite formation has finished here. Okay, so in slow cooling process, that whole austenite structure, your 100% austenite structure, is going to convert it into your perlite structure in case of slow cooling. And when we talk about normalizing process, okay, it is something in the middle. It is in the middle. So we are talking about heating rate of around 20 to 30 degrees Celsius per minute, cooling rate of 20 to 30 degrees Celsius per minute. So here also we can see we are getting the whole phase of perlite. But what will be the difference in both processes in cooling, annealing and normalizing? We are going to get different size of grains. Okay. Here the grain size will be on a little bit on higher side. Here the grain size will be on the lower side. Okay. So coming to quenching process, okay. So when we are going to quench it down, okay. So we have to miss this nose part. What we call this part? We call this part as nose, okay. So we are not giving enough time, okay, or enough high cooling rate, enough lower cooling rate to conversion of austenite to perlite phase, okay. So when we are going with the quenching process, we are not crossing this line, start point of stable austenite, at which it is going to get converted into your perlite phase. So we are missing this nose, and what we will get a new phase which is called as martensite. Okay, so that is also a meta stable, we can say meta stable phase. So here we can see martensitic start temperature and we can see martensitic finish temperature. So when we talk about UTEX steel, this martensitic start temperature is at around 200 degrees Celsius and martensitic finish temperature is at around 50 degrees Celsius. So what you have to do during quenching process, you have to uh, get the temperature down from 7 to 5 degrees Celsius to around 200 degrees Celsius within 1 second or 1.5 or 2 seconds only. Okay, you have just that much of time. So you are going to leave this nose. Okay, you are not going to transformation to perlite structure. You are directly going to transform your stable austenite structure into the martensite. Okay, and this phase is having very high hardness values as we have already discussed compared to this perlite. Now coming to uh, a different phase. Okay, when we talk about bainitic stainless steel, okay, that bainite phase is, it's like the best phase of mild steel. Okay, it is having very high toughness values. It's like if we want to use our steel in aerocraft of applications, then you have to go with, we are talking about only mild steel, we are not talking about stainless steel, then you have to go with magnetic steels because that has highest toughness properties as in comparison to perlitic steel or your martensite steel or other types of steel, mild steel, that has highest toughness values. Okay, so forming that bainite phase, so what we have to do, we have to go like this, we have to quench this up to this temperature and we will hold this, okay, like this, and that then after we are going to just normalize it. So what is happening here, we are missing the no first we are missing the nose. Okay, so we are not getting this gamma plus perlite, sorry, it will not go like this, it will be cooled down from here only. Okay, so you will get some retained austenite and perlite phases in the structure. Okay, so what you have to do, you have to quickly cool down your sample from 7 to 5 degrees Celsius to around a temperature of 400 or 500 degrees Celsius. Then you are again going to put that into furnace at 400 500 degrees Celsius and you are going to hold it for 1 hour or 2 hour according to the desired time, and then you are going to normalize it. So During this process, the trans during this holding time, the transformation will take place from from stable austenite to bainitic structure. Okay, bainite formation. After that bainite structure has formed, it does not matter. You can go with annealing process, or you can go with normalizing, you can go with quenching, you can go with either of three processes, but this bainite structure is not going to get destroyed. Okay, so generally we consider during bainite formation, after this heat treatment process and holding, we generally go with the normalizing process. Okay, because if we are going with quenching processes, then it will create unnecessary thermal shock in our sample. Then after we have to go with tempering and all, we have to provide one more extra heat treatment process. And if we are going with furnace cooling, then we are not then we are going to give that time, sufficient time for uh, getting bigger grain size, so that will also affect your property. So generally we go with the normalizing process. Okay, so now we will discuss some MCQ questions based on phase diagrams and your mild steel heat treatment processes. Okay, any doubt in this? Okay, so we will see. So first question is, which of the following statement is are correct? The heat treatment of steel is concerned with transforming austenite to pearlite. Okay. Then in eutectoid steel, carbon composition is 0.08%. Yes. Statement 1 is correct, but this one is incorrect, because when we talk about eutectoid steel, we talk about carbon composition of 0.8%, not 0.08%. Okay. So this one is right. First only. Coming to next question. Which of the following is a surface heat treatment process? Yes, it is surface heat treatment process. Yeah. Yes. So in yeah. So when we talk about heat treatment process, okay, so we are not providing any specific atmosphere to them or any specific conditions to them. We are just going with the furnace in air atmosphere, or we can go with inert atmosphere if your material is going to get oxidized like that, going to easily oxidize. So we can go with inert atmosphere. But the thing is that the whole sample is going to heat treat. Okay, the properties of whole sample from top to down, or we can say from surface to center, the whole properties of the material is going to get changed. Okay, the hard if we talk about hardness, if we talk about ductility, so the hardness or ductility of the sample will be same from surface to the center of the sample. Okay, so when we talk about some specific applications, like we can say gear. Okay, when we talk about gear assembly. Okay, so what we need some hardness at the teeth of that gear. Okay, so for providing that higher hardness value, but we need ductility inside your sample. Okay, so we just need that property of higher hardness at the surface itself. Okay, so providing that surface hardness, we generally go with surface heat treatment processes. So what we are going to do, we are doping some extra element into the surface of your casted material or whatever type of part you are going with. So we are doping some extra material at surface only until some depth of around, we can say, 500 or 200 microns sometimes. Okay, not more than that. We are going to dope some materials, extra materials into that. Okay, so we need very high hardness. So for high hardness, when we talk about high hardness values, we consider ceramics. Okay, so ceramics are nothing but carbides, metal carbides or metal nitrides. It can be metal borides. Okay, so what we are going to do, we are providing extra nitrogen or carbon or boron, something like that, to our material to form iron carbides at surface only. Okay. So in surface heat treatment process, what we do, we put some extra material, we can say, we can provide it in the either in gaseous form, or we can provide it in powder form also. We are going to submerge our sample with the help of powder. Okay, or and we are going to heat treat it. So during that heat treatment process, what will happen, that carbon on the surface is going to get burned, and that is going slowly going diffusing inside the surface of your sample. Okay, slowly in diffusing inside the surface of sample, and it is making iron carbide, or we can say, yes, it will be going to make iron carbide. Because when we talk about phase diagrams, okay, so as the carbon percentage of your mild steel is getting increased, okay, so hardness value will get increased. So cast iron is having highest hardness values and brittle properties. So what we are trying to do, we are going with 0.4 or 0.3% carbon steel only, and we are going to provide surface heat treatment process or surface carburizing to that sample. And at surface up to some depth of 100 or 200 micron, the carbon percentage can get increased up to 1.5 or 2% or whatever amount you want. Okay, that can depend on the properties what you desire. Okay, you can control your carbon percentage on the surface according to that. So those type of processes known as surface heat treatment processes. Okay, we are, although we are giving temperature to whole sample, but the reaction is happening only at the surface of sample. Okay, and after that, if we are going to normalize it or anneal it, generally we go with normalizing or quenching process after surface heat treatment processes. So your sample is going to create two halves. Okay, at surface the properties will be different, and at center the properties will be different. So these type of processes known as surface heat treatment process, you are trying to increase the properties of surface only. So for surface heat treatment process, we can go with carburizing, we can go with nitriding, or we can go with cyaniding. Cyanide can provide you carbon and nitrogen both. And if you want only iron carbide or only iron nitrides in the system, so you can go with carburizing or nitriding. So what these things are doing, carbon and nitrogen both have very small atomic radii. Okay, atomic radii. So they are going to diffuse inside your sample, and they are going to intercalate into the if we are going in depth, so we can say it is going to intercalate into the voids of your we can say unit cell system or crystal structure system inside the system. So what will happen during that void filling, they are going to provide some stress. Okay, due to that increment in stress, your surface properties is going to get increased. Okay, so these type of processes are known as surface heat treatment process. Okay, understand? Yeah, yeah, you can go with that also, or you can go with first heat treatment process, then you can go with surface heat treatment. because if we are going with surface heat treatment followed by normal heat treatment, okay, so what will happen, you have restricted your sample, your carbon or nitrogen up to depth of 100 or 200 micron. If you are going with normal heat treatment process after the surface heat treatment process, so what will happen, it will get that temperature and your carbon will diffuse more inside the surface of that sample, okay, that will go inside and more inside, okay, that will diffuse more up to more depth into the system. So your properties is going to change up to some level, okay. So first you have to go with normal heat treatment process, then you can go with surface heat treatment processes. Yeah, you can say you have to homogenize that whole sample. Yeah, in surface heat treatment you require some additives, extra additives during heat treatment process, but in normal heat treatment processes you just have to put your sample in furnace and you have to cool it down according to your need, either it can annealing, quenching or normalizing. In cast iron I don't think so surface heat treatment processes is required, because in cast iron you already have very high brittleness, okay. So yeah, you generally go with steels only for surface heat treatment processes. We generally don't go with cast irons because they already have very high brittleness, so you don't want or more brittleness inside system, okay. So the answer is all of above. Now coming to next question, prolonged annealing of white cast iron decomposes the graphite carbon in white cast iron, decomposes the cementite into graphite, decreases the machinability of the component, or both A and C is correct. So we have talked about white cast iron in our previous lecture, and we have talked about annealing in this lecture also. So any answer? Yeah. Okay. So when we are talking about annealing, we have talked about diffusing out of diffusion out. Okay. So your cementite structure is going to break into iron and graphite system. Okay. So the answer is this. It decomposes the cementite into graphite formation, and due to that graphite formation what will happen, that graphite is if you are giving sufficient time, then this graphite is going to get converted into spheroidal graphites, and you are going to get uh, you can say nodular cast iron or ductile cast iron, okay. So that was the process. For that, first you have to make white cast iron, then you have to anneal it, and you have to provide sufficient time to decompose the cementite into graphite and conversion of graphite into nodules, okay. So in that case you can get some ductility, okay, because cementite is more brittle structure compared to your graphite, okay. Coming to next one, which of the following is correct for the annealing process for a ferrous alloy? Heating components to a temperature range 150 to 500 degrees Celsius for suitable period, heating casting to austenitic temperature, holding, and then quenching rapidly. Heating casting to austenitic range, holding, and then cooling in furnace. Heating casting to austenitic range, holding, and cooling in air. So we are talking about annealing of ferrous alloy. Yeah, it is C, because when we talk about annealing, we talk about heating the material above critical temperature 50 to 60 degrees Celsius above critical temperature, that is basically austenitic range. Then we hold it for some time and cooling in furnace. Okay, so answer is C. Coming to next one. In normalizing heat treatment, cooling of casting is done in water, air, furnace or salt solution. Yes. In case of water, we talk about quenching. In furnace, we talk about annealing. And in salt solutions also, we go with quenching processes. So why salt solution in quenching process? Any idea? No, it is not for because we are talking about quenching. So okay, so this salt solution we also in industry the term use brine solution. Okay, so what brine solution will provide? Brine solution will provide high conductivity during your quenching process, and it will uh, not create much thermal stresses into your system. Okay, that will help up to some extent if you are going to quench it in your salt solution. And the main thing, the main disadvantage is water is that if you are going to because water is having a evaporation point of 100 degrees Celsius. Okay, and you are going to put your casting from 900 or 950 degrees Celsius straight into water. Okay, so what will happen? A lot of water will going to get evaporate. Okay, and very high evaporation, um, we can say very high steam generation will be there, and that is not uh, good in your industries because that will create corrosion problem. Okay, your machinery will going to corrode very early. So we generally go with brine solutions or oil. But the disadvantage with oil solution is that sometimes oil catches fire during your quenching processes. So you have to consider safety also in that case. Okay, you have to consider go with very high safety equipments during oil quenching process. So industries generally prefer brine solutions because brine solutions provide better properties as compared to water or oil because it is not going to evaporate that much easier and it will not catch fire also. Okay, so that is the advantage with brine solutions during quenching process. So coming to next one, the increase in the percentage of carbon in steel dash its tensile strength and its ductility. So if we are going to increase the carbon percentage of steel, what will happen to tensile strength and ductility of that steel? D. Okay, so you are saying that tensile strength will decrease and ductility will also decrease. Yes, we are talking about steel. Okay, we are not talking about cast irons. So in case of steel, the carbon percentage is up to 2.08%. Okay, so as we are going to increase the carbon in steel, okay, so up to that 2.08% range, that tensile strength is going to get up. Okay, that will increase and ductility will decrease because as more and more carbon you are adding into the system, the material will tend to form iron carbide. Okay, and if iron carbide content is more in your material, then your ductility is going to get down. Okay, because that iron carbide will influence your ductile properties of the system. So the increase in percentage of carbon in steel increases its tensile strength and decreases its ductility. But when we talk about cast irons, okay, so after that 2.08%, that is a optimized range. Okay, after that your tensile strength is also going to get decrease. Okay, because it will be more more and more brittle in nature after that 2.08% carbon. That is threshold limit. Okay, after that your tensile and ductility both will be going to get decreased after increase in carbon percentage after 2.08%. But but all obviously we are talking about steel in our question. So after 2.08 we generally consider them as cast irons. Okay, coming to next question. Which of the statements above low carbon steel are correct? These steels have a carbon content of more than 2.4%. They are suitable for making sheet, strip and welding electrode. Okay, so when we talk about low carbon steel, okay, we talk about a carbon percentage of around 0.2% only. Okay, so we have three categories from 0 to or we can say 0.05 to 0.2% low carbon steel, then 0.2 to around 0.45 or 0.5%, that is known as medium carbon steel, and after that these are high carbon steels. Okay, or we can divide that with 0.2 to 0.8 medium carbon steel, and after that 0.8 to around 1.5%, that is going to be your high carbon steel. Okay, so according to need of properties, okay, we can decide which type of steel you have to go with. Generally if we talk about stainless steels, okay, then you have to go with some refinement process and addition of alloying elements into the mild steel. Then you will be able to create stainless steel. But in that case the carbon percentage has to be lower than 0.02 percentage. Okay, very lower. Okay, carbon has to be lower than 0.02 percentage for forming stainless steels. So this statement is incorrect because above, if we are talking about more than 2.4% carbon, then it will become cast iron. They are suitable for making sheets, yes, because formability is very high with low carbon steels, uh, because hardness value is on the lower side, or we can make strip, or we can make a welding electrode. Any type of formability applications, we can go with low carbon steels. So the answer is only second. Okay, coming to next one. Eutectic composition in the iron carbon phase diagram has a melting temperature of around degrees. Okay, so we have talked about 3 points in iron carbon phase diagram. One is eutectoid point. Okay, eutectoid points means carbon percentage of 0.8% carbon, and that has a melting point of 7 to 3 degrees Celsius or 7 to 730 degrees Celsius, around that range. Okay, then coming to second one, eutectoid composition. Okay, eutectoid composition was at around 1140 degrees Celsius, with I think 2.06% carbon or something like, no, 0.2% carbon, 0.25% carbon we have eutectoid steels. Uh, this one is eutectic point, sorry, eutectoid points. Then uh, this one is your peritectic point, and this one is your eutectic point. So this has a melting point of around so with when we are going with eutectic steel, so we talk about this line. Okay, so the melting point is at around this 1147 degrees Celsius. Okay, so answer is around 1140 degrees Celsius. Okay, and coming to next one. Which of the following is among the principal elements in stainless steel? sulfur and phosphorus, boron and silicon, chromium and nickel, copper and aluminium. Yeah, yes. We generally add chromium and nickel in stainless steel. Chromium is generally for corrosion resistance properties, and nickel for stabilizing the austenite region. Okay, because we need high ductile properties and high strength. So we have to that stabilize the austenite temperature. Okay, so we can easily get the austenitic stainless steel phase. Okay, and that sulfur and phosphorus, that has not to be the part of steel in any way, because sulfur will create mean cold saltness, and phosphorus will create hot saltness, something like that. And boron and silicon, these are generally used when we require surface heat treatment process. We go with boron and silicon. Okay, and copper and aluminium, these are not at all used in stainless steels. Okay, coming to next one. Which of the following alloying elements primarily imparts corrosion resistance properties in stainless steel? So that is obviously chromium. Okay. So these three are also used in stainless steels for alloying purposes, but the properties of these three are different. Vanadium is generally used for your as a austenite stabilizer phase and grain refinement of stainless steel. If we need lower grain size, then we add some amount of vanadium in our stainless steel. Then if we talk about this is obviously wrong. Then if we talk about manganese, then manganese provides ductility and strength to the system. Okay, this also stabilize our austenite phase, because that is also having, I think, BCC structure. Sorry. Then coming to tungsten, that imparts brittle properties in steel. If you are going to add some tungsten in our stainless steel, generally we don't go with tungsten in stainless steel as alloying element. But if we are going with tungsten, that will increase the hardness of the stainless steel. Okay. Then coming to next one, which of the following statement is are correct in the homogenization heat treatment of non-ferrous alloys? Homogenization of the compositions occur spontaneously through diffusion. Dendritic segregation associated with inhomogeneity in composition occurs because of thermal and constitutional supercooling. So we are talking about homogenization heat treatment process. So we have talked about one process there. I remember tempering process. In that way, in that case, we were talking about heat treatment in between above critical temperature line and lower critical temperature line. So that was in the range of 723 degrees Celsius to around 950 degrees Celsius range. That G to S line and that line, like, so we were talking about this region. Okay, okay. So in homogenizing treatment, what we do, we in the homogenization heat treatment of non-ferrous alloy, but we are talking about non-ferrous alloys. Generally, homogenization treatment we carry out on aluminium alloys. Okay, when we go with age hardening of aluminium or heat treatment of aluminium alloys, first we go with the homogenization process. So in homogenization process, what we are going to do, homogenization of the composition occurs spontaneously through diffusion. Yes, this is correct, because we are trying to homogenize our system. And dendritic segregation associated with inhomogeneity. Okay, whatever the dendrites formation has formed in the system during the casting process, so and solidification processes in composition occurs because of thermal and constitutional supercooling. Okay, in homogenize, yes, that is occurred during your solidification process due to thermal and constitutional supercooling. If you are going to provide supercooling and chills during our schooling process, then dendrite formation will be there. So answer is both first and second. So that is the end of today's slides. So any doubt if you want to ask? Okay. Yes, we will be having class next week. Most probably we will have a class on casting defects, I think. That is the last topic remain. Okay, no problem. Okay. Yeah. Okay, okay. Thank you, Nagin. Okay, so we will finish this class. Okay. Okay, thank you for joining.